So Jesse is continuing with his third lecture today. Let's go ahead.
Right, so welcome back. This is lecture 3 on minimal submanifolds and spheres. And today we're going to be focusing on the situation in codimension 1. So we won't be dealing with high codimension minimal submanifolds. We'll just be dealing with codimension 1 submanifolds of round spheres, which is to say hypersurfaces. Right, so this lecture is really about setting the stage for next lecture. In this lecture, we'll be talking about both theory and examples, whereas next lecture, we'll talk about how to calculate the Morse index of certain examples, and that lecture will be very technical and in-depth with a lot of bells and whistles. This lecture has 4 parts. First, we'll discuss some preliminaries. This will be just an assortment of facts that we need, a lot of background and some conjectures that I'll mention. Then we'll talk about, we'll also define isoparametric hypersurfaces and spheres. Then in part 2, we'll give some examples. In part 3, we'll discuss the theory and the extent to which isoparametric hypersurfaces in round spheres have been classified. And then finally, that should be Roman numerals 1, 2, 3, and 4, obviously. Then in the last part, we'll discuss the Morse index of these things. Okay, so for now, let M be an oriented Riemannian N manifold. Let nabla bar be the Levi-Civita connection on M, and sigma will be an oriented hypersurface. Okay, by hypersurface, I mean a submanifold of codimension 1. Okay, nu will denote the unit normal vector field. The extrinsic geometry of the hypersurface is encoded by the second fundamental form. And last time we saw the second fundamental form, it was valued in the normal bundle. But now we're identifying the normal bundle with the trivial line bundle. We're going to do that pretty much throughout this talk. We're going to identify the normal bundle with the trivial line bundle. And in that case, the second fundamental form, instead of being normal bundle valued, you can think of it as R valued. And in this case, we call it the scalar second fundamental form. It's given by that formula there. Now, this is a quadratic form. And how do you understand quadratic forms? Well, you can use the spectral theorem and study its eigenvalues. So by the spectral theorem, you know that the eigenvalues are real. Let's give them a name. They're called the principal curvatures. Okay, so the principal curvatures of sigma are denoted kappa 1 through kappa n minus 1. Notice that they're functions. They depend on the point. Okay, so kappa j of p is the jth eigenvalue of the second fundamental form at p. I should emphasize that these principal curvatures need not be distinct. That's going to be an important point that's going to come up again and again. These do not need to be distinct. Okay, there's at most n minus 1 distinct ones. Okay, you can of course summarize the data given by the second fundamental form even further by taking the trace. This gets you the mean curvature, and now the mean curvature is not a normal vector field. We're thinking of it now as a function. Right, again, identifying the normal bundle with the trivial line bundle. So the mean curvature is a function, and it's just the sum of the eigenvalues, of course, because it's the trace. Okay, but for us in this talk, we're not going to be interested in arbitrary Riemannian manifolds M. We're only going to be considering simply connected space forms, which is to say Rn, Sn, and Hn with their standard constant curvature metrics. Okay, again, sigma will be a hypersurface. For now, not necessarily minimal. We need 2 words. First, sigma is homogeneous if it's the orbit of an action of a Lie subgroup of the isometry group of M. Okay, so if there's a Lie subgroup of the isometry group that acts transitively on sigma, we say sigma is homogeneous. We say sigma is isoparametric if its principal curvatures are constant. Okay, so remember these are functions, and so isoparametric means that all of these functions are constant. Okay, and I'm going to use the letter G to denote the number of distinct principal curvatures. So a priori, G is some integer between 1 and n minus 1. Notice that every homogeneous hypersurface is automatically isoparametric, and every isoparametric hypersurface is necessarily minimal or CMC. Okay, by CMC, I mean constant mean curvature, where that constant is non-zero. Because in general, the mean curvature is constant, and that constant is either zero or not zero. Okay, so this is so the isoparametric hypersurfaces clearly form a very distinguished class of the minimal and CMC hypersurfaces, and a natural impulse is to try to classify them, right? This is a constant curvature condition on submanifolds in a sense. That's such a strong condition that you should, maybe hope to classify them. And in Euclidean space, this was done a very long time ago. Okay, in Euclidean space, this was done, almost 90 years ago now. It turns out that, G, the number of distinct principal curvatures, can't be anything, either G equals 1 or G equals 2 necessarily. Okay, and so the classification is very simple. There are either hyperplanes or hyperspheres, that's if G is 1, or there are spherical cylinders. And so that's all the isoparametric hypersurfaces in Euclidean space. They're pretty simple. You can also ask about the classification in hyperbolic space. This was also done a long time ago. This is due to Cartan. Again, the only options are G equals 1 and 2. Every isoparametric hypersurface in hyperbolic space is either totally umbilic or is what's called a hyperbolic cylinder. Okay, the remaining case, of course, is the case where the ambient space M is the round sphere of constant curvature 1. And there the classification is an open problem, which is completely different, sort of unbelievable. And it turns out that in that case, it is possible for G to be something other than 1 and 2, as we'll see. For example, G equals 3 can occur. And as we're going to see very soon, isoparametric hypersurfaces in round spheres can be highly non-trivial. The theory of isoparametric hypersurfaces in spheres is extremely rich. It's always if you haven't seen this subject before, it's you're in for a treat. It's a really sort of wonderful subject, I think. Okay, before diving into some examples of homogeneous and isoparametric hypersurfaces, I want to point out a couple of conjectures in which they occur. So one of these is the pair of conjectures known as the Chern conjectures. So from now on, we'll only be considering the ambient space as the round sphere with constant curvature 1. So if you look at minimal hypersurfaces in the round sphere and you look at the Gauss equation, you'll notice that the condition that the scalar curvature be constant is equivalent to the condition that the square norm of the second fundamental form be constant. And so you can formulate the following conjecture about such things, about compact minimal hypersurfaces with constant scalar curvature. Maybe it's the case that the square norm of the second fundamental form of compact minimal hypersurfaces and spheres with constant scalar curvature, maybe that number can only, is constrained to lie in a discrete set. Okay, so this is not known. Right, so the question is there a discrete set D in the non-negative reals such that every compact minimal hypersurface in the round sphere with constant scalar curvature has its square norm of its second fundamental form lying in D? This would be implied by the following stronger conjecture, which is also open. Is it the case that here I'm missing the word compact. Is it the case that a compact minimal hypersurface in round spheres with constant scalar curvature is necessarily isoparametric? Right? Are the isoparametric hypersurfaces the only ones with constant scalar curvature? Okay, note that isoparametric hypersurfaces do have constant scalar curvature. The hard part is the converse. Okay, so both of these are open problems. Various special cases have been checked. I think this is known when n is 4, for example, but as far as I know, this is still open even when n is 5. Another conjecture that's somewhat relevant to us in various points is Yau's conjecture on the first eigenvalue. So here's a sort of basic question you can ask: which compact Riemannian manifolds of dimension n-1 isometrically embed into the round sphere as a minimal hypersurface? Right, so you know the metric in advance. Is there some sort of Riemannian geometric criterion on the metric that maybe is a sufficient or a necessary condition for isometric embedding? Right, maybe there's some necessary condition that rules out isometric embedding into the round sphere as a minimal hypersurface, right? How can you tell whether your Riemannian manifold can or can't be isometrically embedded as a minimal hypersurface? So for now, let's let lambda 1 of sigma denote the first positive eigenvalue of the Laplacian. Yau's conjecture, which is proposed some 40 years ago, says this: if sigma is a closed embedded minimal hypersurface in the round sphere, then necessarily the first eigenvalue of the Laplacian, first positive eigenvalue, is n minus 1. So the dimension of sigma. Okay, so there are a few results. There are several results in this direction. I'm not going to give a complete history, just I want to mention some evidence. So Takahashi showed prior to the conjecture that in fact the first eigenvalue is at most the dimension. And then Choi and Wang briefly, sort of right after this conjecture was posed, showed that the first eigenvalue is at least 1/2 times the dimension of sigma. So it's pretty close. But how, has this conjecture been verified for any examples? The issue, of course, is that calculating the eigenvalues of the Laplacian is very hard. But nevertheless, for the isoparametric minimal hypersurfaces in Sn, then Yau's conjecture has been verified. Okay, this is the result of a series of papers by these folks. And this was completed in 2016 by the paper of Tang and Yen. And it is now known that for every isoparametric hypersurface, Yau's conjecture holds. So it's still an open question for non-isoparametric hypersurfaces, but I mentioned this anyway. Eigenvalues of the Laplacian will be relevant to us. Okay, so we've been talking about isoparametric hypersurfaces and spheres, but I haven't given you any examples. So let's rectify that. Let's go in order of complexity. We'll start with the simplest ones and then get progressively more complicated. So the simplest example for sure is the equator. Okay, so the equator is what you get when you take the n sphere and you cut it with a hyperplane and Rn plus 1. Okay, let's observe that the equator is a homogeneous hypersurface. Okay, it's acted upon transitively by SON. The stabilizer is SON minus 1. And I want to point out something obvious, but we're going to return to this idea frequently, which is that the equatorial, this equator is given by the intersection of the sphere with the level set of a polynomial. Okay, in this case, that polynomial is pretty simple. It's a degree 1 polynomial, right? It's just a hyperplane. But it's interesting, right? It's you take a real algebraic variety in Rn plus 1, you intersect it with the sphere, and okay, that forms this example. And in this case, the algebraic variety in Rn plus 1 is degree 1. And coincidentally, it seems the equator has one distinct principal curvature. So that's kind of funny. Okay, Jim Simons a long time ago computed the index and the nullity, 1 and n respectively. And it turns out that these are lower bounds. In the following sense, if I have any compact minimal hypersurface in the round sphere, then in fact the index is at least 1, the nullity is at least n, and equality holds in either inequality if and only if your hypersurface is congruent to the equator. Right, so this is an instance of the philosophy that we talked about last time at length, that somehow the index is a measure of simplicity, and you should hope to, or complexity, and you hope to, when the index is low, that your minimal hypersurface is, or minimal submanifold is very simple, and you hope for low index to classify such submanifolds. Okay, so the second simplest example for sure are the Clifford hypersurfaces. They work like this. Fixed natural numbers, p and q, adding up to n minus 1. The Clifford hypersurface in the n sphere is denoted sigma p comma q. It's just the product, isometric product of the round p sphere with the round q sphere of those radii there. We need those radii so that it actually fits in the unit sphere. This is again homogeneous and therefore isoparametric. And again, it is, cut out by the intersection of the round sphere with a real algebraic variety. So in this case, the real algebraic variety F, the real algebraic variety is given by the level set of F at 0, where F this time is a quadratic polynomial. So it has degree 2. And interestingly, sigma PQ has 2 distinct principal curvatures. That's kind of funny. The index has been computed. It's n plus 2. I don't know who to attribute this to, but it follows fairly quickly from the result on the previous slide. And the nullity is what you see there. It's kind of funny that the index doesn't depend on P, but the nullity does. And so again, given that the Clifford hypersurfaces are so simple, they're the simplest minimal hypersurfaces after the equators, you might hope that they show up in various classifications and characterizations, and they do. I'll just mention one. Perdomo showed this. If you have any compact minimal hypersurface in the round sphere, if it's not the equator, then the index of sigma is at least n plus 2. So there's actually this lower bound on the index, and not only a lower bound, there's sort of a gap in the values that the index can take, right? So the index can't be arbitrary, right? If it's not 1, then the lowest it can be is n plus 2. You might hope that the index being n plus 2 characterizes the Clifford hypersurfaces, and that's not known. That's an open question. There are partial results due to Perdomo. I also should have written on the slide, when n equals 3, this is true by a now famous paper of Francisco Urbano. I'll add that to the slides later. Okay, but in general, this is still open when n is at least 4. Okay, so many talks on minimal hypersurfaces will mention those 2 examples, and then you wonder what the next most complicated one is, and I suppose it's a matter of taste as to what the most what is the third most simple example. In my opinion, the third most simple example of a minimal hypersurface in round spheres is the Cartan hypersurface. So to explain this, I want to think of R5 in a funny way. I want to think of R5 as consisting of trace-free symmetric 3x3 matrices. Okay, so R5 is the set of 3x3 matrices that are symmetric and have trace 0. That's a 5-dimensional vector space. And what you know from linear algebra is that SO3 acts isometrically on R5, so it preserves the unit 4 sphere. And the action is by conjugation. Okay, and one of these SO3 orbits is this set here. This is the Cartan hypersurface. This is the set of symmetric 3x3 matrices that are traceless. The norm squared is 1, and the determinant is 0. Okay, this turns out to be a hypersurface in the 4 sphere, where the 4 sphere is in R5, and we're thinking of R5 as these matrices. And this turns out to be a homogeneous hypersurface. And not only is it homogeneous, I should say that it's minimal. All of these examples are minimal. And again, it's cut out by the intersection of the sphere and a polynomial. This polynomial now is just the determinant. And the determinant, if you think about it, is a degree 3 polynomial on R5. Because we're working, it's a degree 3 because we're working with 3x3 matrices, of course. And interestingly, this hypersurface, which is minimal, has G equals 3 distinct principal curvatures. So this illustrates, this was studied by Cartan in the 1930s. And so Cartan knew that G equals 1 and 2 were not the only options for the number of distinct principal curvatures for minimal hypersurfaces and spheres, right? Unlike the Euclidean and hyperbolic cases. The index and nullity have been computed by Bruce Solomon in 1990. They are 20 and 7 respectively. It's a very beautiful paper of Bruce Solomon, and one that we'll return to later in the talk. Okay, finally, the last example I'll mention is in some sense the complex version of the previous example, which was somehow real. So now I want to think of R8 as the set of 3x3 complex matrices that are Hermitian and have trace 0. Okay, this is an 8-dimensional real vector space. And again, we know from linear algebra that SU3 acts by conjugation on V in an isometric fashion. So it preserves the unit 7 sphere. And one of those SU3 orbits are the set of those with square norm 1 and determinant 0. This is a 6-dimensional minimal hypersurface in the 7 sphere, and it is homogeneous. Okay, SU3 acts transitively on it because it's an SU3 orbit. The stabilizer is T2. And once again, it is cut out by a polynomial. This is a typo, that S4 should be S7. Yes, so it's cut out by the 7 sphere and the level set of this, again, degree 3 polynomial. Again, there are 3 distinct principal curvatures. The index has been computed to be 44 and the nullity is computed to be 20. Okay, so these last 2 examples indicate in particular that the study of isoparametric hypersurfaces and spheres really contains some surprises, right? It's not just totally umbilic in examples and products, right? There are really some examples that you wouldn't necessarily think of off the top of your head. So it would be great if we could understand what's going on here. So let's discuss the theory and classification of isoparametric hypersurfaces in SN. One more time, sigma is homogeneous if it's the orbit of a Lie subgroup of SON plus 1. And your hypersurface is isoparametric if all the principal curvatures are constant. So historically, what happened was, these hypersurfaces were studied by Elie Cartan in the 1930s, who proved some really beautiful results about them. He actually classified the isoparametric hypersurfaces with G equals 1, 2, and 3. But then what happened was there was not very much interest, aside from maybe a couple papers here and there, for the next 40 years. So really for some 40 years, the field was relatively quiet. And then in the 1970s, interest was revived in a pretty spectacular fashion by papers of Nomizu and especially papers of Munzner. Munzner proved some unbelievably just sort of spectacular results I'm going to share with you now. And that really revived interest in the subject. So Munzner asked, what are the possibilities for G anyway? We've seen that G can be 1, 2, or 3. Can every value of G occur? Maybe G can be anything from 1 up to n minus 1. What are the possibilities for G, the number of distinct principal curvatures? Munzner proved that for an isoparametric hypersurface in the round sphere, that G, the number of distinct principal curvatures, can either be 1, 2, 3, 4, or 6. 1, 2, 3, 4, or 6 are the only options. This was proved using topology. The techniques used to study isoparametric hypersurfaces are quite amazing, actually. There's classical differential geometry with moving frames. Algebraic geometry is used quite a bit, and even K-theory and homotopy theory have been used. So G can be 1, 2, 3, 4, or 6. It's amazing. All we assumed was that the principal curvatures were constant. There's no symmetry assumption here. And he also showed that the cone on sigma has a very interesting structure. I've been hinting at this structure in the previous examples. Okay, the cone on sigma turns out to be a real algebraic variety. So again, very strange. All we've assumed was a curvature condition, and we're deducing that the cone is algebraic, right? It's cut out by a polynomial, a homogeneous polynomial that we're going to call F. This is now known as the Cartan-Munzner polynomial. And maybe the most striking thing about this polynomial is its degree. The degree of this polynomial is equal to G, the number of distinct principal curvatures of the link. So this polynomial F can either have degree 1, 2, 3, 4, or 6. Sort of kind of amazing, really. Okay, so I'm going to call this result Munzner's theorem A because I have to call it something. Okay, Munzner didn't call these things theorem A and theorem B. I don't know what he called them. Okay, I just have to call them something. So the miracles continue. So let's let capital F denote the Cartan-Munzner polynomial from the previous slide, and let's let little f denote its restriction to the unit n sphere. Then it turns out that the range of little f is the closed interval -1, 1, and the only critical points of little f are plus or minus 1. So to understand this function, little f, in more detail, we're going to study its level sets. And we see that there's this natural subdivision between the level sets at height C in the open interval, -1, 1, and then C at the endpoints. So what happens in the open interval? -1, 1, it turns out that each one, all of the level sets of F are isoparametric. So somehow once you have one of them, they come in these like parallel families, right? You can sort of parallel, you get these parallel hypersurfaces, all of which are isoparametric, all of which have G distinct principal curvatures. And if you order them, let's say in descending order, then it turns out that their multiplicities alternate. The multiplicities are like, could be, 5, 7, 5, 7, 5, 7, or something like that. It could be the case that the multiplicities are the same. It could be that M plus equals M minus. And in fact, that happens when G is, I believe, 1, 3, and 6. But for G equals 2 and 4, the multiplicities will alternate. Moreover, in this family of level sets, there's exactly one that's minimal, and that's the one corresponding to C equals 0. I should say that you actually can find out what these eigenvalues are. In a sense, they're all cotan of some angle. I won't explain this, but there's a fairly explicit formula for these in a sense. Okay, so what happens when C is 1, or what happens when C is -1? What can you say about the level sets? It turns out that when C is 1 and -1, the level sets are minimal submanifolds, this time of high codimension, and these are called focal varieties. And amazingly, the codimension of these minimal submanifolds is given by M plus plus 1 and M minus plus 1. So they're given by the multiplicities of the principal curvatures of the of the other level sets somehow plus 1. It's extremely weird. And finally, I'll mention that there's this very nice geometric interpretation of little f. Of course, we know it's the restriction of the Cartan-Munzner polynomial, but it also equals cosine of G times the distance to V plus. Okay, so in particular, it follows that the distance between V plus and V minus is equal to pi over G, where again, G is 1, 2, 3, 4, or 6. So altogether, we have this picture here. Okay, we can sort of, I shouldn't say foliate, but we can, cut up the sphere into these level sets, right? And we see here we have, this is the minimal hypersurface at height C equals 0. Then you have this family of parallel CMC hypersurfaces going up and down the sphere. And then you have here these high codimension minimal submanifolds. These are the focal varieties of the polar ice caps, if you like. I should say that these focal varieties in particular, I find that they show up in many different areas of differential geometry somehow. Oftentimes these focal varieties just they show up quite a bit in places you wouldn't expect. But anyway, okay. So this is, I hope that convinces you that this is kind of a really beautiful thing. There are even more properties that I neglected to mention that you can find in the literature. It's just sort of one miracle after another. There are all these connections to the quaternions and the octonions and various things like this, Jordan algebras. So again, it would be great to classify the minimal isoparametric hypersurfaces and round spheres, and clearly there's a lot to do here. So first, you might want to look at the subclass of the homogeneous ones. Can you at least classify those? And that's been done. That was done by Xiang and Lawson in 1971. It's a really interesting list. There's 5 infinite families and 9 sporadic exceptions of homogeneous minimal hypersurfaces and spheres. I'll give the list on the next slide. We'll return to this list frequently. But what about the inhomogeneous ones? Can you give a classification in general? So when G is 1, 2, or 3, it turns out that they're all homogeneous. This was proved by Cartan in his paper. This is sort of what this is what he was interested in. He was fascinated by the fact that G equals 3 can occur, and he classified the ones with G equals 3 as well as G equals 1 and 2. So there's only homogeneous ones. So maybe you start thinking, well, for G equals 4 and 6, they must all be homogeneous as well. But no, when G is 4, there are in fact many, many inhomogeneous examples, which is kind of stunning. These were first discovered by Ozeki and Takeuchi, and then Ozeki and Takeuchi's examples were generalized by Ferris, Karcher, and Munzner. The inhomogeneous examples discovered by these people are now known as OTFKM type. their initials, OTFKM type, right? Ferris, Karcher, and Munzner's class included the Ozeki-Takuchi class as a subcase. Anyway, as far as I'm aware, the classification is somewhat complicated, but my understanding is that essentially for G equals 4, either the isoparametric hypersurface is homogeneous, which were classified, or they are of OTFKM type. This was proved fairly recently in 2020. This is a very recent classification. It's due to all of these people, Stolz, then Cecil, Chi, and Jensen made a major advance in 2007, which proved sort of completed the classification for all, but somehow a finite number of subcases. Those finite number of subcases were completed in a series of papers by Chi in 2011, 2013, and finally 2020. What about G equals 6? So G equals 4 is somehow extremely complicated. What about G equals 6? That's an open question. So only 2 examples are known. Both are homogeneous. One is in the 7 sphere, the other is in the 13 sphere. As far as I'm aware, those are the only spheres that can occur. And my understanding is that the G equals 6 isoparametric hypersurfaces in S7 are classified. So the only remaining case is that of the 13 sphere. I should say that for a while, there was a classification that was proposed that was accepted for a few years that turns out to be incorrect. So you'll see references in the literature for a certain number of years to the classification being complete, including in the G equals 6 case, but that's now known to be faulty. So in fact, the G equals 6 classification problem is still open. I believe that the 13 sphere is the last remaining case, if I understand that right. Okay, so we're not actually going to be interested in isoparametric hypersurfaces in general. To be quite honest, we're only going to be interested in the homogeneous ones. But nevertheless, the theory is so, the theories are so tied up that it's important to view the homogeneous ones as in the isoparametric setting, I think. But what are these homogeneous ones? Let's go through these. This is sort of an amazing list. So this is the Xiang and Lawson list from 1971. So when G equals 1, we've already seen these. These are the equators. When G is 2, you get the Clifford hypersurfaces. We've seen those as well. When G is 3, there are only 4. There are exactly 4 homogeneous, or in fact isoparametric hypersurfaces with 3 distinct principal curvatures. There's one in dimension 3, one in dimension 6, dimension 12, dimension 24. We discussed the first 2 of those earlier. The SO3 mod Z2 cross Z2 is the Cartan hypersurface, and then SU3 mod T2 is its complex cousin. You may notice that 3, 6, 12, and 24 are all multiples of 3. What multiples of 3 are they? They're 3 times 1, 2, 4, and 8. The dimensions of the reals, complexes, quaternions, and octonions. That's not a coincidence. These 4 hypersurfaces are deeply tied up with those 4 normed division algebras. They're tied up with RC, H, and O in an interesting way. So for example, the focal varieties for these are RP2, CP2, HP2, and OP2. So what about G equals 4? For G equals 4, there's not finitely many. There are 3 infinite families and 3 sporadic exceptions. So it really does seem as though G equals 4 is somehow the most complicated case. So there's sporadic examples of dimensions 8, 18, and 30, and then these infinite families that occur in odd dimensional spheres. Finally, for G equals 6, like I said, there's only 2. These are the 2 homogeneous ones. These are also the 2 that are known even inhomogeneously. Both of these ones for G equals 6 are connected to the Lie group G2, which is kind of interesting. The 6-dimensional one in the 7 sphere shows up in a natural way in G2 geometry. SO4 mod Z2 cross Z2 shows up in G2 geometry, as does, of course, G2 mod T2. So this is the classification for the homogeneous ones, and we'll return to this. So before going on and thinking about the index, I want to raise just a question that I think is quite interesting. So we've discussed last time how if sigma is minimal in the sphere, then its cone is also minimal. However, sigma is never stable. Right? Sigma is never stable, but the cone could be. The cone could even be minimizing. And so that raises the question of how can you tell when the cone is stable? How can you tell when the cone is minimizing? In general, this is actually kind of tricky. There are, I think, sufficient conditions for this. There are some necessary conditions for this. As far as I'm aware, we don't have really a satisfying necessary and sufficient condition. As far as I'm aware, someone can correct me if I'm wrong on that. But in the case when sigma is isoparametric, the stability and minimizing property of the cone is completely understood. We know exactly which isoparametric sigma have the property that the cone is stable, unstable, or minimizing. This is addressed in a very beautiful paper of Qiming Wang that I'd like to advertise. This paper has, I think, not been as widely read as it ought to be. I believe this paper was published posthumously. Qiming Wang died rather suddenly in a tragic circumstance, and this paper was published after he passed. So I want to give the result because it's kind of enlightening, actually. It's very interesting, at least in the case where sigma is homogeneous. So here are the homogeneous minimal hypersurfaces for G equals 1, 2, and 3. And listed in the right column is sort of the best stability of the cone. So is the cone minimizing, stable, or unstable? What we see is that, of course, in high dimensions, the cone is more likely to be stable. In low dimensions, the cone can't be stable. And then there's this sort of funny intermediate thing which happens. Right, so sort of on the boundary, you see that the cone sort of can become stable and then quickly switches to being minimizing. This is a situation for G equals 1, 2, and 3. For G equals 4 and 6, it looks like this. Again, we see that the low dimensional examples necessarily have their cone being unstable, but the higher dimensional ones are more likely to be, in fact, minimizing. It's very rare, it seems, to have cones that are stable but not minimizing. At least in this class, it's sort of funny. Once they're stable, they tend to be minimizing with just a couple of exceptions. Okay, so I want to move on to the last topic. This is the topic that we'll be concerned about all of next lecture, which is how can you calculate the Morse index of isoparametric minimal hypersurfaces in spheres? What can you say about them? So let sigma be a compact, connected, oriented minimal hypersurface in the sphere. Recall Jim Simons proved that every such hypersurface in the N sphere with constant curvature 1 is unstable. Okay, so what you'd like to do is say, okay, it's unstable, but how far is it from being stable? Can you quantify this? And we discussed last time how this can be quantified by the Morse index. The Morse index is encoded by the Jacobi, is a reflection of the Jacobi operator, and the Jacobi operator comes from the second variation formula. Okay, but since we're dealing with hypersurfaces, the second variation formula is somewhat, actually considerably simpler now, because the normal bundle for us is trivial. We're working with orientable submanifolds in an orientable ambient space. So I'm going to restate the second variation formula from last time, or maybe 2 lectures ago, but in a form that's convenient for hypersurfaces in spheres. So let's let nu be the unit normal vector field along sigma. And so every normal vector field, you can think of a normal vector field as a function times nu. Okay, so I'm going to consider variations that are normal. Okay, and when I have a normal variation, well, the variation vector field is f times nu for some function f on sigma. Then it turns out that the second variation of area is given by this integral. It's the integral of f times the Jacobi operator of sigma, where now when I say Jacobi operator, I mean the Jacobi operator is acting on functions of sigma, again, because of this identification between the normal bundle and the trivial line bundle. So the Jacobi operator of sigma on f is just the Laplacian on sigma. Notice that that's intrinsic to the geometry of sigma plus the square of the second fundamental form plus n minus 1 times f. So this is, again, this is a second order strongly elliptic operator, and it's the Laplacian plus 0th order terms. Okay, so my convention for the remainder of this talk and also all of next talk is that the Laplacian for me is negative definite. Okay, so my notation for the Jacobi operator is that its eigenvalues I'm going to denote by mu. There are some negative Jacobi eigenvalues, then there's the eigenvalue 0, and then there's infinitely many positive ones. This is a real sequence that goes to infinity, and the multiplicities I'm going to denote by L. So L1, L2, etc. LS is the multiplicity of the 0 eigenvalue. And recall that the Morse index and nullity are sums of these multiplicities. So the Morse index is the sum of the multiplicities of the Jacobi operator corresponding to the negative Jacobi eigenvalues, and the nullity is the multiplicity of the 0 eigenvalue. And the problem, again, is to compute the Morse index and the nullity, and in general, this is hard, and by hard, I mean completely hopeless. Right? This is just completely intractable in general. If I just pick a minimal hypersurface at random, we're just not going to be able to do that. Okay, but maybe you can do this in a special case. Maybe if sigma is isoparametric, there's more hope. And in fact, when sigma is isoparametric, the situation really simplifies. It simplifies because this 0th order operator is now just a constant. So the 0th order term is, well, it's a constant times the identity, if you like. So the Jacobi operator simplifies. It's now just a shift of the Laplacian, okay, in the isoparametric case. So for isoparametric hypersurfaces in spheres, the Jacobi operator is just a shift of the Laplacian. So knowing the spectrum of the Laplacian is sufficient to compute the index and the nullity. So all you have to do is find the spectrum of the Laplacian. The thing is, though, even when sigma is homogeneous, computing the spectrum of the Laplacian can be highly non-trivial. I think there's a misconception, I think, among in the geometric analysis community that maybe, oh, if you have a homogeneous Riemannian manifold, computing the spectrum of the Laplacian is just really easy. That's known. No. When your homogeneous space has a normal Riemannian metric, what's called a normal Riemannian metric, so it's induced by the killing form in some way, then yes, there is sort of a representation theory procedure to compute the Laplacian. That's fine. But if the metric is not normal, then in general, we have no idea. In general, the spectrum of the Laplacian is extremely hard. And in fact, for the homogeneous minimal hypersurfaces and spheres, those metrics are generally not normal. So this is really not trivial. Okay, so computing the index and the nullity amounts to computing the spectrum of the Laplacian. Let's look at this in the homogeneous case again. So what is known? So in the homogeneous case, for G equals 1, 2, and 3, we do know the Morse index and the nullity by virtue of knowing the spectrum of the Laplacian in this case. So when G is 1, this is due to Simons. When G is 2, I don't know who to attribute this to, but this is essentially a corollary of Simons' result. Then it took some time before the G equals 3 case was addressed. This was addressed in a pair of papers by Bruce Solomon in 1990. The first paper addressed the first two examples, dimensions 3 and 6, and the second paper addressed the 12 and 24 dimensional example, and these are the indices and nullities that he computed. His method is going to be very important for us. We'll explain it later. Okay, so then after 1990, there was sort of no movement on this table. For G equals 4 and G equals 6, none of these Morse indices or nullities were known. Okay, so since 1990, there was sort of no progress. This table for G equals 4 and G equals 6 was completely blank. So all this blank space got Uwe Semmelmann and Gavin Ball and I to talking. We thought, we should really start chipping away at this table. And so we got very interested in this 8-dimensional exceptional hypersurface SO5 mod T2 in the 9 sphere. And we were able to show that this 8-dimensional minimal hypersurface in the 9 sphere has Morse index 275 and nullity 35. Okay, so this is the first result that I'd like to advertise. We also considered these infinite families, and we're still thinking about those. It would be great to get the index of these infinite families. What would be interesting is if you could run some sort of induction argument. We don't know whether if an induction argument will work. That's what we're sort of thinking, maybe it could work. But if you're going to do an induction argument, you're certainly going to need the base case as part of that. So for the first infinite family, the base case turns out to be corresponds to k equals 3. The index is 39, and the nullity is 11. Okay, and so this table now represents, as far as I'm aware, the state of the art. Every entry that's blank is an open question. We do not know the Morse index and nullity of any of these other entries at all. So there's a lot of room for progress. So I want to explain the results that I just mentioned in slightly more detail. And I, in particular, really want to contrast the two examples that we looked at in the G equals 4 setting with those in the G equals 1, 2, and 3 setting, because somehow it's really radically different in sort of a striking fashion. So when G is 1, 2, and 3, what Jim Simons and Bruce Solomon were able to do is they were able to get essentially an explicit formula for the eigenvalues of the Laplacian, right? So they were able to essentially parameterize the eigenvalues of the Laplacian, right? There's some polynomial with integer coefficients, and you can sort of just plug numbers into that polynomial and out come the eigenvalues of the Laplacian, right? There's a formula for them. And that formula, because it's this polynomial with integer coefficients, it shows in particular that the spectrum of the Laplacian, when G is 1, 2, or 3, consists of integers. But our examples are somehow quite different. The G equals 4 examples that we looked at. So, I mean, first of all, we weren't able to find a formula. That's the first thing I should say. We weren't able to find a formula in the sense of Simons and Solomon. What we do is we produce an algorithm that generates the eigenvalues and their multiplicities. So what do I mean by an algorithm? So remember, the Laplacian is negative definite. Here's what I mean. You give me a number, -1,000, right? And our algorithm spits out all the eigenvalues of the Laplacian from 0 to -1,000. Okay, and then you give us -10,000 and we give you all those eigenvalues, right? And more precisely, what we do is if you give us -1,000, the algorithm spits out a finite list of finite dimensional matrices. And then the eigenvalues of those finite dimensional matrices, those eigenvalues will be the Laplace eigenvalues from 0 to -1,000, as well as some others, that are beyond -1,000, but for sure, at least you got the ones in the range you wanted. You might say, okay, well, that's kind of disappointing. Why didn't you get a formula, for the Laplace spectrum? That would have been far more satisfying. But we think that maybe there's a good reason for that. And the reason is that for our examples, the spectrum of the Laplacian doesn't just consist of integers. There are integers for sure, but there are also irrational eigenvalues, some of which are not expressible in radicals. So that kind of combination suggests that maybe a formula is pretty unlikely. So just for illustration, to illustrate this kind of mix of order and chaos, I want to show you what the Jacobi eigenvalues end up being, the non-positive ones. So it turns out that when G is 4, there's always this arithmetic progression of non-positive, very short arithmetic progression of non-positive Jacobi eigenvalues. This was not due to us. This was observed in a separate paper of Bruce Solomon. Okay, so a third paper of Bruce Solomon, and he pointed this out, that there was always this sort of arithmetic progression of non-positive Jacobi eigenvalues that you see there. What was unclear was whether there were any others. For all we knew, those were all the non-positive Jacobi eigenvalues, but in fact, we now know that in these two examples, at least, there are others. So what are those other non-positive Jacobi eigenvalues? Well, you can all see the pattern. They're exactly what you think they are. Of course, they're 4 radical 5 minus 20 and 24, and 4 radical 7 minus 20, and these sorts of really wild things. So it's this very strange mix of order and chaos. Here, I should say that 14.2, this is expressible in radicals, so is -4.6. It's just the radical expression is so gigantic, I just didn't want to put it here. So the irrational eigenvalues that are not expressible in radicals, those are on the positive side of the Jacobi spectrum. Okay, so this gives us the index and nullity as a corollary. Of course, you don't just need the eigenvalues, you need their multiplicities. So that's what we do. For each of these eigenvalues, we know their multiplicities. So if you add up these multiplicities, you get for these numbers, you get the index. And similarly here, you add up these, you get the index. And these two, of course, are just the nullity. Okay, so this is what we get. So how do we do this? How we do this exactly is going to be the subject of next lecture. But very briefly, what we do in outline is we follow Bruce Solomon's technique. So we take Bruce Solomon's technique, which was successful in the G=3 case. We refined it a bit. We made it sort of more of an algorithm, more systematic in a sense. And we also extended it. We broadened its scope slightly. So this technique is a 4-step process. So in each of these steps, I should emphasize, is very non-trivial. So sigma is a homogeneous, hypersurface. So let's say it's G mod H. So step 1 is to consider the L2 functions on sigma. And you're going to want to decompose that space into G invariant pieces. Okay, these W1, W2, etc. These are called isotypical summands. Okay, you do this with the aid of a theorem called Frobenius reciprocity, which I'll explain next time. That theorem only somehow gives you half of the story. It sort of tells you what these spaces are, but it doesn't tell you their dimensions. And calculating their dimensions is actually quite tricky. You need some input from representation theory, so you call up your representation theorist friend and maybe they tell you what the dimensions of these are. Okay, then the second thing you have to do is for each of these WJs, you need to find an explicit, what we're going to call a generating basis. So a generating basis is not literally a basis for WJ. It's going to be a basis of a very small subspace of WJ. But despite being a basis of such a small subspace of WJ, because of the G invariance, that ends up being sufficient to compute, that ends up being sufficient when you're calculating the spectrum of the Laplacian. So you want to find an explicit finite set of functions, B sub j, such that Wj is the span of not the f's, but f composed with g's. Okay, so this is where the geometry really comes in. This is somehow the most geometric part of the 4-step process. This is where you really need to know something about the geometry of the objects that you're working with. Okay, and then in step 3, because of the nature of this generating basis, to find a matrix of that represents the Laplacian, it just suffices to compute the Laplacian on these functions that make up the generating basis. So what you have to do in step 3 is just calculate the Laplacian of f and express the result in terms of the generating functions. And at first blush, that seems really easy. I thought when this project started that this would be, very simple. I mean, I can compute a Laplacian. How hard can that be? And of course, you can compute a Laplacian. The problem is that you have to express the Laplacian in terms of the functions you started with. And that ends up being very non-trivial and actually very hard. That requires a sort of some clever tricks that my collaborators thought of. So I'll explain that later in the next lecture. So the result of steps 1, 2, and 3 is that you now have an algorithm that generates the eigenvalues of the Laplacian for you. The problem is you have no control over where those eigenvalues live, right? At the end of the day, if you're interested in the Morse index, you don't need all the eigenvalues. You just need, the eigenvalues in this range. You need the eigenvalues in the range -g times n-1 to 0. But how many WJs will give you that? Do you need to calculate the, this for 1 billion WJs? You only have finite time. So when do you stop? You need to know when this process is supposed to terminate. And so that's what step 4 does. In step 4, we essentially provide this upper bound. We show that on WJ, all the Laplace eigenvalues have this upper bound. And the point is that if this upper bound is less than or equal to -g times n-1, then WJ has no eigenvalues relevant to the Morse index. That criterion, as simple as it sounds, actually rules out all but finitely many of the WJs, which is the point. And so this reduces finally the entire calculation to a finite linear algebra calculation. you're left at the end of the day with a finite list of finite dimensional matrices. Okay, so that's the method in broad strokes. And this is what we'll talk about next time. But I do want to advertise right now just some future directions that we're sort of hoping to go in. So one thing we'd like to do, of course, is to apply this method to the other minimal hypersurfaces in the spheres, right? There are the other homogeneous minimal hypersurfaces on that list. We'd like to run the induction argument, for example, and see whether we can calculate the Morse indices and nullities. Not clear whether we'll be able to do this. Some of these are on the list are really very daunting, but we will see. But we also feel somehow that this method is quite powerful and quite general. You may notice that nothing about this method assumed that your homogeneous space was actually a minimal hypersurface of a sphere, right? All this method assumed was that sigma is a homogeneous Riemannian manifold. So this method in principle could work for any homogeneous Riemannian manifold, which is quite exciting, including the non-normal ones. So maybe it's possible to apply this method and calculate the index of some, highly symmetric minimal submanifolds of high codimension. There are some challenges in doing that. We will see whether that's possible. Finally, it would also be great to apply this method to compute the index and nullity of certain symmetric free boundary minimal hypersurfaces in the unit ball. So these wouldn't be homogeneous. Maybe these would have some other type of degree of symmetry like homogeneity 1. Here, the method would be applied somewhat loosely. Here, I'm being a bit, generous with the phrase application of the method, but certain aspects of the method may carry over. So we will see. Maybe we can use this to compute the index and nullity of some free boundary minimal hypersurfaces in the ball. These are all things we're talking about. We'll see what comes of it. Anyway, I look forward to seeing you in the next lecture. Thanks for your attention.
Thank you very much. Any question? Yeah, thanks for the nice concrete examples.